Welcome to the Nodal Analysis Masterclass. If you are an electrical engineering student, you know that some circuits are easy. Series, parallel, Ohm's law, done. But then, you meet the monsters. Circuits with multiple loops, multiple sources, and bridges that defy simplification. Attempting mesh analysis here is a recipe for algebra mistakes. We need a better tool. We need a universal solver. We need Nodal analysis. Before we write a single equation, we must understand the physics. Nodal analysis is based on one simple fact. Voltage is not absolute. Voltage is a potential difference. Think of it like height. I can't say this ball is at 10 meters unless I define where 0 is. This is why the first step in any circuit problem is to place our ground. This is our sea level, our zero reference. Here is the 4-step algorithm. Memorize this and you can solve any linear circuit. Step 1. Identify all nodes and pick a reference node. Usually we pick the bottom wire because it connects the most components. Mark it with the ground symbol. It is now 0 volts. Step 2. Label the remaining non-reference nodes with voltages V1, V2. These are our unknowns. Step 3. Write Kirchhoff's current law for each non-reference node. Remember, the sum of currents leaving a node is 0. Step 4. Solve the system of linear equations. Let's apply this. Here is a circuit with 2 current sources and 3 resistors. Step 1. Ground the bottom. Step 2. Label node V1 and V2. Step 3. Let's write KCL for node 1. Imagine you are standing at node 1. Currents act like water flowing downhill to lower potentials. The current going down through R1 is V1 minus 0 divided by R1. The current going right through R2 is V1 minus V2 divided by R2. The current generated by the source is entering. Since we sum currents leaving, we write minus 5 amps. So our equation is V1 over 2 plus V1 minus V2 over 4 minus 5 equals 0. Now for node 2. Standing at node 2, current left, V2 minus V1 over 4. Current down, V2 minus 0 over 6. Current source is leaving, so we write plus 10 amps. Equation 2, V2 minus V1 over 4 plus V2 over 6 plus 10 equals 0. 2 unknowns, 2 equations we solve. Now, a warning. Nodal analysis loves current sources. It hates voltage sources. Why? Look at this circuit. We have a 10-volt source connecting node 1 and node 2. If we try to write KCL, what is the current leaving node 1 through that source? Is it V1 minus V2 divided by resistance? No. The resistance of an ideal voltage source is 0. Determining current this way involves dividing by 0. Establish a rule. If a voltage source sits between 2 non-reference nodes, we create a supernode. Imagine enclosing the source and both nodes in a bubble. We write KCL for the entire bubble asterisk. Any current leaving node 1 or node 2 external to the bubble is summed to 0. The internal current is ignored. But wait, we lost an equation. We have 2 unknowns but only one KCL equation. We need a constraint equation. Look inside the bubble. The source forces a difference. If the positive terminal is at V1, then V1 minus V2 equals 10. That is our second equation. Solved. To recap, first, ground your circuit. Choose a reference node, usually the bottom. Second, label your nodes V1, V2, V3. These are your unknowns. Third, sum currents leaving equals 0. Apply KCL at each node. Fourth, use supernodes for floating voltage sources. I've left a practice problem on the screen. Can you find the current Ix? The solution is in the description below. Master this method, and no circuit will ever intimidate you again. Thanks for watching.